4.6, we're going to be working on composite figures. In this particular section, we're going to be asked to find the area of a certain geometric figures. Each geometric figure is going to be made out of two or more geometric figures that we learned previously. For example, in number 1, it seems to be a rectangle in a semicircle. Number 2, a rectangle and 2 semicircles. Number 4, a triangle and a semicircle. So previously in chapter 2 and chapter 3, we learned how to find the area of those triangles or the area of those rectangular figures. So number 4.6, we're gonna do everything combined. So I'm gonna start doing problem number 1. In problem number 1, they're asking you to find the area of the region, give the exact answer, and then round it off to a nearest thousand. So I'm gonna graph what I have there. Seems like this figure is gonna be composed of a rectangle and a semicircle. So my artistic skills are not that good, so we're gonna have to be doing a few things here. Let me see. I'm gonna have here, I'm gonna try to make a nice rectangle. Here you go, a rectangle and a semicircle. So these measurements here is 6, this measurement here is 13 feet. So everything is in feet. I'm probably gonna write here feet. Now to find the area of all of these, I need to know the area of that rectangle here and as well as the area of this circle here. So the total area, I'm gonna put area total, right? Everything is gonna be composed by a rectangle who has dimensions of 13 by 6 plus this semicircle with a given radius. Now we know that the area of a rectangle is base times height. We know that the area of a semicircle is what well, the area of a circle is pi half squared, so half of a circle is going to be 1/2 of that. So, but we need to know the radius, and we don't know it yet. However, if I go back to my picture, look what happens here. If this is a rectangle, then it means that this side is 6, and this side is actually the diameter of the circle. Therefore, its radius should be 3 feet. Also, my radius is equals to 3r equals to 3 because the diameter was 6. Now, let me put my formula. So the formula for the area is going to be base times height for the rectangle plus the area of a circle is pi r squared. But because I have half a circle, that should be 1/2 pi r squared. Now let's go back to this problem here. Area of the total area, the base is 13 times the height is 6 plus 1/2 pi r squared, which in this case is 3 squared. Doing this algebraically, let's multiply these two numbers here, which is 13 times 6. 13 times 6 give us 78. So this part here should be a 78 plus, recall the this 3 squared is actually 9. Okay, this one here is 9. So 9 times 1/2 is 9/2. So I should be able to have 9/2 pi. But they want you to give this the exact solution. So I'm probably going to combine these two things together. I'm going to put it in the same denominator. This could be an okay answer, but I believe they want you to put it all together. So let's do this here. Let's just simplify everything together. So it means this is going to be over 1 times 2 times 2, so I can have the same denominator. So 78 times 2 is going to give me 156 over 2 plus 9/2 pi over 2. 9/2 pi. So all of these combined, I put in the same denominator, 2 and 156 plus 9 pi. And do not forget about your units. We're talking about feet, so I could either write feet with a power here square, or you can just write a square feet. So this is the exact answer. Now if I want to find my approximate solution, I have to crunch everything on the calculator. So 8 total approximated. So this curly one means approximated. So I'm gonna have 156 plus 9 pi in my calculator divided by 2, and it should give me 92.137, what else, 1669. But how many digits do I need? Well, the instruction says give the exact answer and then round it off to a nearest thousand. So I'm gonna look for the thousands place. Tens, hundreds, thousands. So the thousands place is here. So I'm gonna do my barrier here, and because they say round off and this is just a 1, so this should be approximately 92.137 square feet. So it's 92 and 137 thousandths square feet. So this is gonna be my approximate solution. So that was for problem number 1. So usually in these figures, we don't really know the figure of this. That looks like a bullet. We don't know the area of it. We don't know exact formula. So we gotta decompose that. That's made out of a square, it's a rectangle, in which the area of a rectangle is base times height, and of a semicircle, which is half of the area of a circle. So that's how these figures are gonna be now. Like number 2, you'll have to decompose that as same thing. Number 2, you have to decompose it, as well as number 4. Let's try number 4. So here we have an equilateral triangle topped with a semicircle. So number 4, I'm gonna try to rewrite it again. Well, let me just decompose this. So number 4, since we have it here, so you have an equilateral triangle with a semicircle. Equilateral means that these sides are gonna be the same, right? This is 6, this is 6, this is 6. So I'm gonna have what? My area, the total area, is actually gonna be decomposed into things: an equilateral triangle plus a semicircle. And put it this sign so we know that's an equilateral. Another thing that we know about equilateral has 60 degrees, right? To be equilateral. Now, in this semicircle, who should have a radius of, we don't know it yet. Can we find it? Maybe. All right, let's do one thing at a time. So let's find the area of this equilateral triangle. To find the area of any triangle, we need to know the base and the height. Well, I know the bases, but I do not know any height. So maybe what I can do here is I'm going to project this part here, tracing altitude, which is going to give us, look what's going to happen here. It's going to give us this part here. Look, we're going to have a right triangle here with degree 60 and degree 30 here, and this long side, well, this hypotenuse or the diagonal is, that hypotenuse should be 6. So we need to find this part here. How are we going to find it? Recall that we used to do these special triangles in the previous chapter. So you're going to have a 30 degrees, 60 degrees, and 90 degrees right triangle, which this one was the hypotenuse, the small angle opposed to the small side, and this is going to be the long side. We're practically looking for the long side. And also remember that hypotenuse is equals to 2s, and L is equals to s root 3. To find L, I need to know s. Therefore, let's find s first. Hypotenuse is 6. S, we don't know it, but we divide it by 2 each side, and we get s is equals to 3. Now that I know s, I can find L. So L equals to 3 root 3, and everything is measured on centimeters. So I'm going to put here centimeters, so we know everything is in centimeters. Okay, and this long side actually happens to be the height that we need. So I'm going to rewrite this nicely here. So maybe I'm going to have here my triangle now, here, with a height of 3 root 3 and the base 6 plus, so now we have enough information to find the area of this triangle. Now, do we have enough information to find the area of this semicircle? We still need to find the radius. So let's look carefully at this circle here. Actually, this part here is 6. All of this is 6. The diameter is 6. And recall, the diameter, I'm going to write this nicely. Recall that diameter is equals to twice the radius. So if the diameter is 6, then the radius is half of it. So therefore, radius is equals to 3. So my semicircle is actually half of a radius, half of a circle with radius 3. Now, then I'll write then the total area, A subtotal, is equals to, let me write the formula. Recall that for the triangle is going to be 1/2 base times height plus, well, because it's a semicircle, recall that this is a semicircle. It's a semicircle. The area of a circle is pi r squared, but because it's a semicircle, you're going to have 1/2 pi squared. Now, we have every information here. 1/2, base in this case is 6. The height is 3 root 3 plus 1/2 pi r squared, which is 3 squared. Now, this 3 squared happens to be 9, so just keep that in mind. And I'm going to reduce here. 2 goes into here once, 2 goes into here 3 times. So the total area is going to be equals to 9 root 3 plus 9/2 pi. As we did previously, I need to simplify this. I'm going to put everything in a single fraction. So I'm going to put this over 1, multiply times 2 each side. So I'm going to have an exact solution. I'm just going to do this on the side. That's going to give us 18 root 3 over 2 plus 9 pi over 2, which is exactly, I'm going to put here, area, the total area is going to be 18 root 3 plus 9 all over 2. And what units do we have? Centimeters squared. So this is my exact solution. Now, if I want to find my approximate answer, I'm going to put A total is approximately, and we have to crunch everything on the calculator. So I'm going to put 18 square root of 3 plus 9 pi. So plus 9 pi, I forgot to write that, 9 pi. So the pi just didn't disappear. So it was 9 pi over here. 9 pi. And let's see what the calculator is going to give us. 9 pi over 2. And we're supposed to get about 29. So the calculator says this is 29.725624. I'm just writing everything that the calculator is giving me. But the instruction says round off to the nearest thousand. So I'm going to locate the thousands place. So tens, hundred, thousands over here. And because this is more than 5, this is going to be approximately 29.726 square centimeters. And this is the approximated solution. Okay, so in this particular problem 4, we have to decompose this one here, this figure, into a triangle who was equilateral triangle with side 6. Each of them has 60 degrees. We needed to find its altitude plus the semicircle who had radius 3. So in this particular section, we're going to apply everything we learned in this chapter and what we learned in the previous chapter to find the areas of a given region. Let's keep moving on to the next following problem. So in this problem number 6, they say find the area of the shaded region. So previously, what we did in number 1 and 4 was some areas that were composed by two figures. But in this case, whenever they want you to find the area of a shaded region, most of the time we're cutting things. Like for example, here it looks like we had a full square here. We had a full square. All of these is in a square. And then what we did with this, that's why we cut this circle, this half circle, this half circle, and this half circle. So to find the area, like cutting is going to be like subtracting it. So that's what we're going to be doing in this particular problem. So the shaded region, I'm going to write here. So shaded region, area of the shaded region equal to, we're going to have that square here that we have to find the total one minus 4. I'm going to put times 4 here on top, times 4 over these semicircles, who we know should have some radius r. Do we know the dimension of these squares here? I'm going to put these marks so I know these are squares. So the dimension is 14 millimeters. So I'm going to write here mm, so we know, as a reminder, that's our unit. So the area of the square is easy to find. We can do it. But how are we going to find the area of these semicircles? Well, actually, also remember, look what's nice about this. 4 semicircles actually makes 2 entire circles. So just keep that in mind. Now, knowing that, we still need to find the radius. So let's see how we can do here. If I know that these semicircles are cut each in the middle of it, so if this is 4, the middle here should be r, and this part here should be 4. So to find r, I'm going to write here, to find r, we're going to need to use that all of this here is actually 14 millimeters. So 4 plus r plus 4 should be equals to 14. So 8 plus 2r should equals to 14. So we're going to be getting here a 14. Minus 8, 2r equals to 6. And r should be equals to 3 millimeters. Now I have my r. So it means I can use everything on the formula here. So the shaded area is going to be, well, let me write the formula here. S squared minus, in this part here should be twice, because I'm going to have 2 areas of these circles, pi r squared. And I have r and I have the side, so we have everything here. So I'm going to probably move this here. I'm going to say area of the shaded area subshaded, equal s, in this case, which is 14, being a square, minus 2 times pi times radius square. So I'm going to have 14 square. I believe that's 196. That should be 196. But let's double check that. 14 square in case we have a miss something. So yeah, 14 square is going to be 196. 196. And also recall that this part here, you're going to have 3 square is actually 9 times the 2 that you had in front. It should be 18 pi. So that should be our exact solution, because you cannot combine them. It's like having like terms. This is an 18 pi. You cannot do anything there. So you say all of these is my answer, but do not forget about your units. So be millimeters square, or you can write square millimeters. So the shader region, because they want you to approximate it, so I'm gonna crunch all of this in the calculator, minus 18 pi, and that should give me about, it says here, I'm gonna copy what it says in the calculator, 139.451332. So, but we still need to run to the nearest thousand. This problem says run off to the nearest thousands. So I'm gonna locate the thousands place. So tens, hundred, thousands. So because this one is not more than 5, so I'm just gonna stay there. So this is approximately 139.451 square millimeters. So that's how we're gonna find the area of this shader region. We're gonna take the entire square, and then we're gonna apply its square, like those squares here, those circles here, that we have to get rid of it. So all of these squares minus the circles. In problem number 7, they're asking you to find the shader region again, but in this case, it seems like we're gonna have the entire square, and we're just gonna cut the circle in the middle. Let me read the problem first. It says a circle 23 centimeters in diameter. So they are giving you the diameter of the circle, which is from one end, from this end to this end, should be, that passes through the center as well, should be 23 centimeters. And it's inscribed. So I want you to recall, to remember, you must memorize this part here. Inscribe. One of the ways that I remember the inscribe, what does inscribe mean? Inscribe means is inside a figure. Like, look at this, ins here, inscribe inside. So a circle inscribed in a square is a circle inside a square. Okay, just pay attention to these wordings. You're gonna need it. You're gonna need to know, just in case that they don't give you the figure. So you're gonna have to, draw it yourself. So how am I going to find the area? Once again, we say that the shaded area, we don't have to decompose this. The shaded area is actually the area of the square. So this is in a square. I'm gonna draw in a square. Sides are the same, and each of them is 90-degree angles. Minus, I will take away the area of a circle who has a given radius. Do I know the side of the square? We don't know it yet. So let's find it one by one. If the diameter here is 23 and this is the circle, and the circles inside this square, what I mean is, like, this part here is 23 as well. From here to here is 23. So it's telling you that the size of this square is going to be 23. This one actually is equals to 23. What about the radius? They are telling you that the diameter is 23. If the diameter is 23, if d is equals to 23, and the diameter is equals to twice the radius, if I divide by 2 each side, then I'm going to get the that the radius is equals to 23 over 2 centimeters. And I'm just going to put cm here to tell us that we are working with centimeters. So let me write my formulas now that I have everything. So I'm going to write the area of the square is s squared minus pi r squared, because it's just one square. S, which is 23, being squared, minus pi r, which in this case is 23 over 2 square. That should give us our exact area. 23 squared. Let me use a calculator and see what it is. 23 square is 529. So I'm going to write here 529 minus, I want you to be very careful here because this square here, whenever you have to distribute for each of them. So I'm still going to have the pi there times 23 squared, which happens to be 529, over 2 to the square is 4. So I'm going to have here over 4. So let me move all the way here. So we will have that the shaded area, A shaded, is equal to 529 minus 529 pi over 4. But I want to simplify this. I want to put this all together. So what I'm going to do here, recall that this is over 1 times 4 top and bottom. Let's see what we're going to get. This 529 times 4 give you 2,116 over 4 minus 529 pi over 4. Then we get that the shaded area, the shaded region, is going to be 2,116 minus 529 pi, all of these over 4. But do not forget about your units. So this should be a square centimeters. I also want you to find the approximated solution. So the approximated answer, I'm going to have to crunch everything on the calculator. That 2,116 minus 529 pi. And then I'm going to divide this by 4. And I should get, I'm going to write, the calculator says 113.52437. And the instruction says that I must round it to a thousands place, tens, hundred, thousands, up to here. So round off, this is not enough, so I'm gonna have, this is approximately 113.524 square centimeters. So once again, for this particular problem, number 7, we had a circle that was inscribed, which means that is inside this square. And if I want to find the shaded area, the shaded region here, what I needed to do is find the area of this entire square and then take away this part here in the middle, like make a hole there. And that's how we will find the shaded region. Let's do problem number 8. Circle circumscribe about a square. So also I want you to remember the circumscribe means outside. Okay, so I'm gonna also rewrite it here. Circumscribed means like outside, surrounding it. I'm just gonna put outside because recall previously we did the inscribe, means like inside. Circumscribe is gonna be around it. Okay, circumscribe about a square of a side 28 feet. So if it's circumscribe about a square of side 28, I'm going to write that given information here. So I'm going to write this is 28, and because it's in a square, this is 90 degree, 90 degree, 90 degree, 90 degree. Each side is 28, 28, 28, 28. So to find the area of this shaded part, I need to find the area of the total one, the bigger picture here, which is, I'm going to write A shaded here. A shaded is going to be equal to the area of a circle with a given radius r, I'm going to call it r, minus that square in the middle who has a size 28. So I'm going to write my square here, equal sides. All right, so this is easy one. We have that one, but we do not have the radius. How am I going to find the radius? Well, there's probably something that we can do with this 28. Recall that this is in a square. If from here to here is 28, for every side is 28. So the center is around here. And from here to here, be careful. From here to here is 28 as well. But this is not the radius. So I want you to be aware of that thing, because this is not 28. From here I mean, this is not the radius. This is just 28. The radius is actually, so this is not, I'm going to just erase this part. Actually, the radius should be from here to here. And from here to here, combining from this point to this point, happens to be the diagonal of the square. And at the same time is the diameter of the circle. Let me write that down here. I'm going to say then the diagonal of the square, is actually the diameter of the circle. Can we find the diameter of the square? Yes, I can, because it's in a square, and a square is like a, if I put here, this is going to be like 45, 45, 45, 45. So let me clean this up. Let me have this all clean. I'm going to clean it and do it again because it's all messy. So here should be the diagonal of the square with the center, and this should be 45, 45, and this is 90 degrees, and this was 28. So now there I see my 45, 45, 90 special triangle. So to find the diagonal, I'm going to use that 45, 45 triangle. So 45, I'm going to write 45, 45, 90 triangle. I'm going to draw it here just so we have a better view of this. So 45, 45, and this is 28, 28, and this is the diagonal, or as we used to call it, the hypotenuse, right? Let me find the hypotenuse. Also recall that hypotenuse is equals to L root 2, and because L is given, that should be 28 root 2. Yes, now I have the diagonal of the square, because this is actually the diagonal. And also happens to be the diameter of the circle. So this is also 28 root 2. And now this all, but how am I going to find the radius? Well, if I know the diameter, I can find the radius, because if this is the diameter, I'm going to write here, this is the diameter again. I'm pointing it out. This is the diameter, and the diameter is equals to twice the radius. So 28 root 2 is equals to 2r. If I divide each side by 2, I'll get that r equals to 14 root 2. And we're talking about feet. So that's something that I forgot to write here in big. We're talking about feet. So now I have the radius. So now I can find this area, and I have enough, all the information that I needed. So area of the shaded region is equal to, well, I'm going to write my formula first. The formula for the area of a circle is pi r squared minus, well, for this square is going to be s squared, equal, now pi r, which we just found out, is 14 root 2 square minus s, which is 28 square, equal, now be careful here. I want you to, I still have my pi times, but this is square here. Be careful. You have to distribute for each of them. So that's actually, I'm going to write here in red so you are very aware of that. Times the square root of 2 to the square. Minus 28 squared. I can do that in my calculator. I crunch that on the calculator, and I get that this is 784. Now I'm going to do this part here. Square root of 2 to the square is, this part is 2 times 14 squared. What is 14 squared? Let's use the calculator for that. 196 times pi, and all of this here is going to be 392 pi minus 784. So that should be the exact solution of the shaded region. But do not forget that all of this has square feet. Now, one of the questions the student asked me is, Why do we need to put parentheses here? The reason is, if I don't put the parentheses, so if I say this 392 pi minus 784 square feet, if I just say that, I'm actually saying this. That is 392 pi without units minus a square feet minus 784 square feet. So this square feet will actually only be affecting this guy here. So that's why we need to put the parentheses in here. So this will affect to both of them, and it will actually say 392 pi square feet minus 784 square feet. So that's why we put the parentheses in between them. Okay, so I just wanted you to be aware of that. If you do not write that, your answer might be considered wrong. Okay, so we need that parenthesis is so important because you want to say that the units for all of that is a square feet. And we're very, very careful in geometry. If we don't write our correct units, we might not receive full credit for the given problem. Even though you did all the work, probably you only receive partial credit for it, but you don't want to risk any points in your test. Okay, knowing that, let's keep going and find the approximate solution, because this was the exact solution. This is the exact solution or the exact answer. So now let's find the approximate solution. So A shaded is approximated. Well, let's climb everything in the calculator. Let's put everything in the calculator here. 392 pi. 392 pi minus 784. I'm writing on the calculator, and the calculator shows that I get 447.50432, so on. But the instruction says that we must round it to the nearest thousands, tens, hundreds, thousands, up to here. You check if this guy is 5 or more. It's not, so it means you stayed. So the shaded region is approximated 447 and 504 thousandths square feet. So that's the final answer. You're gonna give your exact answer and your approximated solution, and also remember to find the region, the shaded region. We needed to subtract an entire circle and then cut or make a hole inside. That's what we're subtracting that square. Problem 13. In problem 13, they want us to find the area of an annulus whose outer radius is 8 centimeters and inner radius is 3. So when we're doing this particular problem, what they want us to do is, like, we're gonna get this 13, right? Problem 13, they want you to find the area between the annulus. Well, the annulus is pretty much, let's see how that figure. It's a bigger radius circle here, and then we have a small circle here. They both have the same center. Okay, so the area of that is pretty much this part here. Like, let me shade it with this way. It's pretty much this part here, like the donut, kind of like a donut. Okay, or like a whisker. I mean, what do they call like dishwasher, like a dishwasher. So a donut or dishwasher. That's the area that they want you to find. Like when you cut a bagel, you see that area, that space there. So that's what they want you to find, the area of it. How are we going to find that area of the annulus? Well, the area of that is that actually, if I decompose that as we did previously, the area of the annulus, actually, I believe you can just find the area of the annulus by saying with a given formula, or we could derive the formula of that problem. Now, what are we going to do here? I prefer to break this down as a large circle. I want to do a big circle, the area of the big circle with radius 8, minus the small circle with radius 3. So let's recall, what is the area of a circle? It's going to be pi r squared. So in this case, it's going to be pi. In this one for here, r is 8 squared minus pi 3 squared. The area of this annulus should be equal to 64 pi minus 9 pi, which give us, let's put here, this gives 64 minus 9. What is 64 minus 9? You can either do it in your calculator or you do it mentally. 64 minus 9 is actually 55. So I'm going to have 55 pi, because they want you to find the exact solution. It's going to be just 55. So area of the annulus is 55 pi. And what units are we talking about? I forgot to write it here. It should be centimeters. So it should be centimeters square or square cm. Okay. Now, but they also want you to approximate it. So I'm going to write here exact. This is exact answer. And the approximate solution is going to be, so I'm going to put it's approximated. I'm going to use the calculator, multiply that by pi. 55 times pi is going to give us 172 point, I'm going to write all of it, 787595. Round to the nearest thousand, so I'm going to find 10th 100,000 is here, so I'm going to have 172.786 square centimeters, and this is the approximated answer. So now let's do problem 15. Problem 15 say, find the area, right, of a 45-degree sector of the annulus in exercise 13. So it's the same annulus here. So, but to find the sector of an annulus, the area of a sector, we first need to find the area of the entire annulus. So we're going to need the information for 13. So I'm just going to rewrite it here. I'm going to put here, and I'm going to have to write area of the annulus. I'm going to rewrite it here. Area of the annulus, of the entire annulus, is equal to 55 pi square centimeter. And I'm going to erase this part here, so I get the problem here. So let me erase this. So now that we erase that, so I'm gonna draw my sector of the annulus. So it's pretty much gonna be a piece of it. Like if you were cut, it's gonna be something like this. Something like this. And this part here is gonna be 45 degrees. Let's just assume that it's 45 degrees. How are we going to find the area of this annulus, like the space inside here? How am I going to find this area? What we need to do is we need to do our same technique as we used to your arc length. We're going to apply the same thing for the area. So I'm going to put here sector. I'm going to use this structure like the table and entire annulus, like the whole annulus, entire annulus. So, and here on top, I'm going to have the degree measurement. So you must memorize how we use this thing. Measurement, measure. And here we need to put the area here. So what is the degree of the sector? It's 45. What is the degree of the entire annulus? The degree of the entire annulus is 360, because we're talking about the whole thing. Now, what is the area of the sector? We don't know that. That's going to be our x. That would say we're going to call it x. And what is the area of the entire annulus? Well, in the previous problem, we found that. That's 55 pi. So we're going to use proportions here. So whenever we get 45 over 360 degrees equal to x over 55 pi. So degree and degree will go away, so pretty much don't need that degree here. Now let's cross multiply this, or recall that you can just multiply times 55 pi and everything is, and the x is by itself. So 55 pi times 55 pi each side, and this one will go away. So you don't really need to cross multiply this. So just times 55 pi each side, and we're gonna have to reduce this. Let's reduce this. So does 45 goes into 360? Maybe. Let's double check that in our calculator. 360 divided by 45. Yes, that went 8 times. So I could have reduced that here. So I'm gonna say goes 8 once, and this goes 8 times. So pretty much we're left with 55 pi over 8. That should be the area of the sector annulus. So the area of the 45 sector annulus should be that. That's the exact solution. So I'm gonna write here area of the 45 degree sector annulus, sector of the annulus, is 55 over 8 pi. If I want to pi, what? We're talking about square centimeters. So approximately, I'm going to use my calculator and write 55 pi divided by 8, which gives me 21.59844. Round to the nearest thousands, 10 hundred thousandths. I will get that this is approximately 21.598 square centimeters. So this was the exact solution, and this is the approximate solution. I also want you to be aware that just 15 could be an entire problem. So maybe they could ask you, find the area of a 45 degree sector of the annulus that has an outer radius of 8 centimeters and inner radius 3 centimeters, inner R and R8. So they could ask you that. Okay, they could ask you just 15. So first, what you needed to do is find the area of the entire annulus, and then find the area of the particular sector. Or also, they could tell you, find the area in the perimeter. So how would I do the perimeter? So we learned that in the section 4.3, I believe, when we started talking about, it was actually section 4.4 when we talk about circumference. So let me just do it as a bonus problem here. I don't want to mess everything here. I'm going to make in a space here. Find the perimeter of this annulus. This is so important. I want you to pay attention to this part, because you probably really need to emphasize on that. That usually in the tests or any quizzes, they ask you to find the perimeter in the area. So maybe they will ask you to find the perimeter of this annulus. So the perimeter will be the sum of this plus this plus this plus this. Okay, so do we know this part here? Well, if all of this was 8 and this is 3, then this part should be 5. So I have a 5 and a 5 here. Oh, but then I need to find the outer arc length and the inner arc length. So I might not have enough space to do that. So I'm going to erase this, and I'm just going to find the perimeter. As a bonus problem here, I'm going to try to find the perimeter of this annulus. So let's do it again. I'm going to erase all of this and just find the perimeter of this annulus. Let me erase everything. Perimeter, we need to find the arc length of this outer arc and the inner arc. So for that, we're gonna have to use, let me first call this probably let's call it what, small c, bigger c. I don't know what we can call this, but let's see what the book calls it whenever it refers to. I think they just call it X and Y. So I'm gonna call this big one X, and I'm gonna call the small one Y. So I want to first find X, which is the arc length of the outer one, right? So first of all, whenever you're doing this part here, they recall the arc length is similar to the circumference of it. So whenever I'm going to be doing that, we're gonna do our table, or we're just gonna write here. We're gonna write sector. Let's think about first the outer circle, okay? The big circle. I'm gonna focus on the big circle, so means I'm gonna do the outer arc length. So the sector is going to be here, and then I'm gonna put here a full circle. I'm gonna write here full circle. And here on top is gonna go the degree measurement. So I'm just gonna write degree. And here is gonna go the arc length. So what is the degree of the sector? 45 degrees. What is the degree of the first circle? 360 degrees. What is the arc length of the sector? We don't know that. We call that X. And what is the arc length of the first circle? It's actually the circumference. And a circumference of this given problem is 2 pi r. Also recall, circumference of any circle is 2 pi r. For the one that we need to find, we're looking for the one that is 8, right? The r is 8, so it's 2 pi times 8, because we're doing the big circle with radius r. Probably going to write here r equals to 8. So using proportion, we have 45 degrees over 360 degrees equal to x, and everything at once. 2 pi times 8 should be 16 pi. I'm going to have to multiply each side by 16 pi to leave the x by itself, times 16 pi times 16 pi. This is gone, and I'm going to have to reduce. 45 goes into 45 1, and 45 goes into 368 times. Yes, it goes 8 times. So I did everything at once here. Then I'm gonna have to go 8 goes into here once, and 8 goes into here twice. Let me double check that. Hold on. 45 goes into 360. I'm gonna have 360 divided by 45. Yes, that was 8 times. So we had it correctly there. So I'm gonna have I'm gonna have left 2 pi. So here is 2 pi equals 2x. So that means that this part here should be 2 pi. So I had a typo here. So this is 2 pi. Now, in the small circle with radius 3, I'm going to use the same technique. Sector, full circle, degree, and arc length. The sector is 45 degrees. The full circle is 360 degrees. The arc length is y in this case. Be careful here. The small circle is 2 pi and the radius is 3 here. Now using proportions, you have 45 degrees over 360 degrees equal y over 6 pi. Then I'm going to have to multiply each of them by 6 pi. 6 pi and by 6 pi over here. And I will have, let's see what we're going to have left with here. This is gone. This is gone. I could apply the same approach here. 45 goes into here 1, 45 goes into here 8 times. So, and I probably can reduce his part here. These numbers, half 3, half 2, and then therefore 3 pi over 2 is equals to y. So everything's in centimeters. So if I rewrite this neatly, I'm going to have something like this. Well, the 45 is here. The annulus 45. My arithmetic skills are not that great, but here should be 2 pi, and this guy here should be 3 pi half, and this should be 5 and 5. Therefore, the perimeter P is equals to 5 plus 2 pi plus 5 plus 3 pi half. Perimeter will be 10 plus 2 pi plus 3 half pi. And let's find the exact answer. I gotta put everything together. So over 1, and each of them times 2, times 2, times 2, times 2. This is actually equal to 20 over 2 plus 4 pi over 2 plus 3 pi over 2. All of this together is going to give me 20 plus 7 pi over 2 centimeters. So this is my perimeter. So if I want to find the approximate solution, I will have to put this in my calculator. I'll put 20 plus 7 pi, all of these divided by 2, and give me 20 point. And the question says round to the nearest thousand. So in the calculator we have 99. So 9955. 10 100,000 place. Let's do 10 100,000 up to here. Seems like we're gonna go one more digit up. Therefore, this is, I'm gonna write it here. I have no space, so therefore this is approximately 20.996 centimeters. This is approximate answer. Okay. Approximate. So this could be a problem. I mean, a full problem probably could be number 15. Find the area in the perimeter of a 45-degree sector with annulus with outer radius 8 centimeters and inner radius 8 centimeters. So be aware of this problem. This problem you have to pay a lot of attention and could practice more. Keep practicing this problem. Do a similar problem. Probably do problem 14. Find the area of the entire annulus, then find the sector, and then find its perimeter. So you're gonna have to practice more and more of these problems. Let's do one more problem. As I said before, sometimes in a problem they're just gonna give you a sentence and they're not gonna give you the picture, so that's gonna be much harder. Like in 24, a circle is inscribed in a regular hexagon of size 6 feet. Find the area of the region between them. Before, they used to give us a picture. Now we have to draw it ourselves. So for that, we must understand the language of it. What does inscribe? Circle is inscribed. Recall that I say inscribe means inside. So you're going to have a circle inside a regular hexagon. So let me picture that up. Let's see how I'm going to have. So I'm going to have an hexagon here. Probably something like this. Imagine that's a regular hexagon. And I'm going to have a circle inscribed. So probably... Okay, this is not good looking. So what I'm going to do is I'm going to draw my rectangle, my circle first. I'm going to put my circle here first. And then I'm going to do this. So I'm going to try to be as... Let's see. Hexagon here, somewhere here. So you get the idea. Okay, so we're trying to have an hexagon like this, a regular hexagon, and they want you to find the area here inside. So you want to find the area here in between. So you get the idea that we're trying to look for this part here. All right, so how are we going to do this? Well, first I need to know the area of the hexagon, and I gotta chop this circle. So the area of the shaded region, the area between them, the area that we want to find, I'll call it the area of the shaded region, I'll call it that, is going to be the area of the hexagon, the regular hexagon here, minus the area of the circle with a given radius. So, well, first to find the area of the circle, I need to know at least the side, right? One side, say the side is 6 feet, so everything here is in feet. So this will be 6, this will be, so every side is 6. But recall that to find the area of a regular polygon from the previous chapter, area of a polygon, area of a regular hexagon, sorry, regular hexagon or polygon. In this case, we're looking at this hexagon. The area of a regular polygon is usually 1/2 the apothem times the perimeter. So this is gonna turn out to be one problem like the previous chapter that we work on. So let me just focus on finding this area. Do I have the perimeter? Yes, I could find it because it's a regular hexagon, so we can find that, right? So do I have the apothem? The apothem is this measurement here, right? So for that, you needed to break this into triangles. Remember, we had a triangle, each of them is 120. Therefore, this part here is like an equilateral triangle. So I'm gonna zoom in the equilateral triangle there. This is 6. This is gonna be a square root, and here's gonna be the apothem, right? So it's gonna be 60, and this is gonna be 30, and this is actually 6, and because this is in equilateral, this is 6 as well. So let's find this part here, the 8. And if we recall our 30, 60, 90 degree special triangle, what I'm going to have this part here is like the hypotenuse, and this is the long side, and this is the short side. And recall the hypotenuse is equals to 2 small side, and the long side is s, the short side is square root of 3. So hypotenuse equals to 2 times s, which is, we don't know. Well, the hypotenuse, we actually knew it. Hypotenuse is 6 equals to 2s. Then, therefore, s is equals to 3 if you divide each side by 2. Now I have enough to find the L. L equals to 3 times the square root of 3. Now, in actually this length side, this long side is the apothem, right? This is the 8, the apothem. So I almost have enough things to find my perimeter. I had the apothem, but I do not have the perimeter. How do I find the perimeter of it? Perimeter is equals to, how many sides does this have? This is n equals to 6. So I'm going to have 6 sides times each side is actually 6. Therefore, my perimeter is 36 feet. Now, do I have enough things to find the area? Yes. So let's leave that for a minute. Okay, because here you're going to have area of the shaded region is 1/2 AP. You have enough information here. The area of the circle is pi r squared. Do we have r? If this is the center, and from here to here is 6, and also remember, like from here to here as well was 6. Look, remember from the apothem, whenever we're looking at here, from here to here is also 6. No, that actually is the apothem is 3 root 3. So that part here is 3 root 3. That's the apothem. The apothem actually happens to be the radius as well. So we know the radius. Therefore, the radius, I'm going to write here for the radius is equal to the apothem. I believe I'm writing it correctly. So, or r equals to a. R equals to a is 3 root 3. Now let's just do this part here. I have everything to find my shaded region. 1/2 a, which is 3 root 3, times the perimeter, which is 36, minus pi r, which is 3 root 3, being a square. So I'm going to have to do all of this. A equals to a little bit of algebra here. 2 goes into here once, 2 goes into here 18 times. 18 times 3 is 54. So I'm going to have 54 the square root of 3 minus, be careful here. I always say be careful in this part here. You're going to distribute. So it's going to be 3 squared times the square root of 3 squared. Let's see what's that. Pi times 9 times 3 equal 54 root 3 minus 27 pi. And because you cannot simplify this any further, all of these is your exact area of the shaded region, or the area in between the regular hexagon and the circle. So, but do not forget about your units. The unit should be here square feet. And they also want you to find the approximated solution. Well, they did say it from problem 13 to 26. Find the area of the region described and make sure you draw a picture. We draw a picture and give the exact answer and round it off to the nearest thousand. So I'm gonna have to round this to the nearest thousand. This is approximately. I'm gonna apply my calculator and say, let's see, 54 root 3 minus 27 pi. That gave us 8.70774. Round to the nearest thousand. It's gonna be tens, hundred, thousands. We might make my barrier there. This is approximately 8.708 square feet. So this is your approximate answer, and this was the exact answer. The one here is the exact answer, and this is your approximate answer. So that is the end of the chapter as well. This is 4.6. You're gonna have to apply all the tools that you learned in the previous sections as well in the previous chapters to find the area of the given polygons or the given figures. So I would recommend you to review and master, and you must memorize those formulas. That's why every single time that I'm writing a formula for the area, I try to rewrite it. So in that sense, like here, I wrote it again. In that sense that we memorize those things. The point here is to memorize as many formulas as we need to know, because that will, if you do not know the formula, there is no way you can keep moving forward in this particular class. You must memorize the formula for every single area, for every single geometric figure, so as well as the theory about them. Memorize your 30, 60, 90 degree angles, memorize the 45, 45, 90 right triangles. So all of these are going to come in handy whenever you're going to be working in this particular chapter, as well as for the rest of the semester. So just keep practicing. Now I believe you could practice your test. So just do your best and redo one problem over and over and over until you master it, or select a problem that looks similar to this.